Let us write the allowed vibrational energy levels. Now we turn to the vibrational state functions. Giving the expression for the functions, it is convenient to use a dimensionless variable. Dimensionless. That I call y, which is x divided by some parameter called alpha, where alpha is h bar square divided by force constant times reduced mass to the 1/4 power. Don't bother about this definition here, but simply remember that the original variable x has a unit. What unit does it have? Distance unit. If y, as I claim here, y has no unit, that means the alpha parameter should also have distance, same distance unit as x. So this is distance unit here, and y is dimensionless. Now the vibration state functions which correspond to each energy as a function of this y is a normalization constant multiplied by a function, a polynomial, times an Gaussian function. This is normalization constant. This factor is called a Hermite polynomial. And this expression is not the exponential function, because this is y squared here. Exponential function contains, as in the exponent, just the first power of the variable. This is called Gaussian function. Look, e to the minus x, let us say y. So this is y-axis. Such a function has graph like this. This is exponential function. But a Gaussian function, such as this one, because it is y squared in the exponent, it has a bell shape graph. This is e to the minus y squared. So a Gaussian function, therefore, is a function very different from the exponential function. This is values for the normalization constant are given in the notes. The V subscript here is indicating that value for the normalization constant is different for different V. Okay? Now, the Hermite polynomials are well-known polynomials in physical chemistry or math textbooks, or if you go to internet, type Hermite polynomial, you will obtain millions of websites which discuss the properties of such polynomials. But I'll give you some examples. These are few of these, but of course there are expressions for larger values of V also. These can always be found from the physical chemistry textbooks or mathematical textbooks or from the internet. What is significant about these expressions? You see that these are polynomials. What is the highest power in the polynomial? In the first one, highest power is 0. In the second one, highest power is 1. In this one, highest power is, for y, what is it? 2. You see, highest power in the polynomial is the same as this index. Same thing is true here. Highest power is 3. This is a general property. It is a polynomial of degree. The highest power in a polynomial is called the degree of the polynomial. Another property of these polynomials is that, let us first indicate that range of y is between plus infinity and minus infinity. Both negative numbers and positive numbers are available for this variable y. Now, these polynomials have certain property when you change y to minus y. This one, the first one, is the same for either, because it's independent of y. For negative y and positive y, it is the same. When a function has the same value for positive values as those for negative values, how do we describe such a function with respect to 0? We call it even function. So this function is even. The next one, this one, when you change y into minus y, the sign changes in the function. Those functions that have this property are called odd functions. So this is odd. What about this one? Because it is y squared here, it is even, isn't it? And the next one, odd. So this is a general property for these Hermite polynomials. Look, if the index subscript is an even number, 0, 2, then 4, and so on, the function is even. On the other hand, if the subscript for the polynomial 1, 3 is an odd number, the function itself is an odd function. This is something relatively easy to keep in mind. Therefore, Hermite polynomials have this property, that if the subscript index is an even number, the polynomial is an even function. On the other hand, if this index is an odd number, the function is an odd function. Now, come to here. This function, in terms of even-odd property, does it have a property? This Gaussian. If you replace y with minus y, does the value change? No. You see the graph also here. It is symmetric. So this is an even function. This is even function, and it is the same factor for all Hermite polynomials. As a result, we can say something about the total function. The total function is Hermite function times this Gaussian factor. All right? The total function is either an odd function or even function, depending on just v here. If v is a even number, the vibrational total function is an even function with respect to y. On the other hand, if v is an odd number, the vibrational function is an odd function. Such information that we notice about these functions can be useful. For example, say we want to calculate average value of the x variable. Definition is all right. It is this, from minus infinity to plus infinity. Now, if you know that psi is an even function, then psi times this factor is also even. But there is also x variable here, times x will make the total quantity to be odd function, but the limits are symmetrical. The integral of an odd function over all space will give 0, because half of it is minus, half of it is plus. When you add up the total, you get 0. So in our example, calculate the value of y. Notice that these functions are real functions. There is no complex number I in them, purely real. So we have y at the vibration level v, psi v square times y times dy. So what do we conclude for the value of this integral using this property? Square of this expression will always give an even function. Whether it can be odd or even, but when you take the square of it, it's always even. So this is even. Psi square is even. But y is odd. Odd times even gives odd. And the integral of an odd function over all space is 0. So this saves you from doing the integration explicitly. So it's very useful information. So what does it tell us? The average value of y variable in all vibrational states for all V is 0. All right. Let us show the graphs of these functions, or rather squares of it, on the vibrational potential energy. So let us write this as y. Now I'm first drawing my harmonic potential. This is energy axis. And then I mark the energy level value starting with the lowest one. So this is 0.5 F0. Now I draw a axis which is parallel to this axis, but vertically it passes through the lowest energy level. This is V equals 1, V equals 0 level here, all right? This way our graphs, when we look at the graph, we will also be able to know which energy vibrational function that is. We are drawing this. This is probability density function. The first one is for V equals 0, because this is just 1 here. In such graphs, the numerical value of the normalization constant is not important. You can just drop it. So what remains is just this factor, e to the minus y squared over 2. Take the square of it. You will get e to the minus y squared. This is psi 0 square. Omitting the normalization constant. So the graph of it, the qualitative, this is psi 0 square, graph of psi 0 square. Now, let us compare the situation quantum result here with classical expectation. Classically, at this energy, the vibration takes place between this point, called this y0, and this is minus y0. These are the classical turning points at this energy. We had discussed that. Classically, if this vibrating particle has this energy, then maximum extension is this point. It cannot proceed further to the right. And also, this is the left turning point. Now we compare it with the quantum result. According to quantum theory, the probability density gives us multiplied with dy will be probability. Probability of finding the particle at some value for y. We see that this point probability these are the y values after the right turning point. At such y values, is the probability density 0? You see the graph here. Value at this this height is measured from the origin here. This is 0 for the height. And this is 1 if we just draw this expression here. Now, 0 is exactly on the axis, but this curve is above it. Therefore, is it 0 or not? Say, at this point, at this value, you see the function value is not 0. The function value becomes exactly 0 only for when y goes to infinity. So the value for y values which are larger than the right classical turning point, the probability density is not 0. What does it mean? Probability of finding the particle at a distance larger than the classical turning point is non-zero. Classically, is it possible to find such a particle with this energy at y value which is larger than the turning point? No. Classically, it cannot. But quantum mechanically, because this wave function is slowly going to 0, there is a non-zero probability for finding the particle at a distance larger than the classical turning point. This process is called quantum mechanical tunneling. So the probability of finding the particle outside of the classical turning points is called the tunneling probability. Just as in here, on this side, on the left turning point, again, there is a non-zero probability for finding the particle away from the classical turning point. We may calculate the probability of finding the particle at a distance or outside of the classically permitted region. Classically permitted region is y between y0 and minus y. These are the turning points. But for y larger than y0, according to our quantum result, there is a non-zero probability. So, how do we calculate that? Total probability or probability for y larger than y0 on this side is let me write this in general. Psi v square times dy from y0 to plus infinity. This is the probability this is the expression for finding the total probability of finding the particle on this side. Now, according to this graph, I would use the function psi 0 here. But for other v values, this is our expression. Now, probability for finding it on the left side, y less than is when we write these expressions, we arrange the limits such that the variable increases from lower limit to upper limit. So here I write minus infinity to minus yt, minus y0. Okay, so let's make this y0. So this is psi 0 square. Because square of the wave function is an even function, but changing the variable of integration, you may see that this expression is same as this expression above, because psi 0 square is an even function. All right? You use the property of integration. Therefore, the total probability is 2 times this expression. This gives the total probability of finding the particle outside of classically allowed region, both the right side and the left side, both. Which means this is the tunneling probability. Now, the function here that we use must be normalized function. In other words, the correct value for the normalization constant must be given. Otherwise, probability interpretation doesn't work. The actual integral is, this is 2 normalization factors there is a square root of pi after when we take the square of it, times psi 0, this is e to the minus y square, and for this function, this is 1 to infinity. Y0 is 1 for the lowest vibration level. Now, such an integral doesn't have an analytical solution because the lower limit is non-zero. If the lower limit were 0, there is a standard result for the value of the integral. But whenever this is not 0, the lower limit is not 0, there is no recipe for the indefinite integral. Such integrals are calculated using numerical methods, and either a calculator or a computer. There are standard numerical methods, so I have used one of them to calculate the value of this integral, and I have obtained the value 0.157. Now, what does this mean? converted into percentage, multiply with 100, 15.7%. There is 15.7% probability that the particle will go out of the classically limited region, which is a large probability, isn't it? 15.7% for the lowest level. For other levels, we can also do calculations. Now, for the next level, V equals 1, this is 1.5. Now, we pass a axis similar to this one, which is parallel to. Now, we draw the graph of psi 1 square. In other words, for V equals 1, the graph looks like now the turning point with this energy is this value. This we call minus y1, and this the turning points are labeled by the vibration quantum number V. So at this vibration energy level, there is also a certain probability for finding the particle outside of the classical region, because it is equal to the area under this part times 2, because the same contribution comes from there also. And I have given you two more examples. When you use psi 1 square to do the calculation, one gets 11.2% tunneling probability. As energy goes up, tunneling property decreases according to our calculation. For example, with the next state function, the tunneling property is 9.5%. The largest is for the ground level. All right, this should be enough for the vibrational wave functions. Let us briefly discuss light absorption by the molecules, which cause a change of vibrational state. Now, the light frequencies which are used to study vibrational transitions must contain vibrational frequencies near this is light frequencies should be near vibrational frequency. And I had given an example for HCl molecule. It was 2,900 something wave number unit. Now that region is called infrared region. So infrared spectroscopy is used to study light absorption, which causes change in the vibration states. The first rule is that diatomic must be heteronuclear, or the diatomic molecule must be polar. This means if you take a homonuclear molecule such as H2, O2, N2, such molecules do not absorb infrared photons. Only for polar type molecules, when the two atoms are different in the diatomic, infrared photons will be absorbed, such as hydrogen chloride or hydroxide, OH. Those are heteronuclear diatomics, and they will absorb infrared, but not homonuclear. Now, if it is a heteronuclear, then there is a vibration selection rule. I will write it generally. This is for absorption. And this is for emission. Delta V means the change in the vibrational quantum number can only be 1 unit. Now, if we consider a sample of gas molecules, and we are assuming they are heteronuclear molecules, we know that we have just done a calculation that vibrational distribution is such that all the molecules are in the lowest vibrational level. Therefore, when you shine light, the only possibility is absorption. And all the molecules are in V equals 0 level. Initially, there are no molecules in the excited levels. All the molecules are in the lowest vibration energy level. So initial vibration quantum number of all molecules is which number? V equals 0. The selection rule is V can only change by 1 unit, which means the molecules initially, because initially they are all in the lowest V equals 0 level, if they absorb a photon, the only possibility is this transition. There is the transition from this level to that level, for example, is not allowed. The only allowed transition is which satisfies delta V equals +1. This is written generally because there may be cases where by some means the molecules could be generated in the excited vibration levels, and then you may study absorption and emission from such a sample. Then, if there were some molecules, say, at V equals 2 level, then those molecules could, if they absorb, they would make a transition to V equals 3 level. But if they emit because they are excited, they have excess energy. If they emit, they make a transition to V equals 1 level. This is what it means, V minus 1 for the emission. All right. Now, when we study infrared, we have to now think about, because photon energies are large relative to the microwave. We have to think about the fact that besides vibrational motion, the molecule is also rotating. And the infrared photons will cause a change in the state. Both it could change, it could cause a change in the vibrational state as well as rotational state. We have to think about such possibilities. So now I'm going to combine the vibrational motion with the rotational motion to answer this question. Hep şurada şey var diye bakıyorum, ondan dengemi kaybedeceğim. All right. Here is a molecule. One atom here, one atom there. That's vibrational motion. All right? During this vibrational motion, the molecule is also rotating. So it's complicated. Both the vibrational motion and the rotational motion keep center of mass fixed. Center of mass is fixed in space, and that means that point doesn't move during either rotation or vibration. There is this vibration, and at the same time, there is rotation. Now, I'm not going to prove it to you, but it can be shown that this complicated simultaneous motion of rotation together with vibration can be separated into two independent motions. One is vibrational motion that we discussed, and the other is the rotational motion we have also discussed. In fact, it is because of such reasons we have taken one by one, because I knew that the two motions could be separated. Separation means physically this. The vibrational motion has no effect on the rotational motion, or opposite. The rotational motion has no effect on the vibrational motion. This is an approximation. In reality, they do affect each other, but the consequence is small. Therefore, because it simplifies everything, we consider the vibration and the rotational motion as independent, not affecting each other. So, in this approximation, in this good approximation, the rotational vibrational Hamiltonian, rho vip, is equal to sum of rotational Hamiltonian. Remember, our rotational, the independent variables for the rotation were two angles, the polar angles, theta and phi. So this is a function of theta and phi plus vibrational Hamiltonian. This is theta phi x. The total number of variables is how many? 3. These are independent variables. X is independent from theta and phi. X ranges from minus infinity to plus infinity. Theta from polar theta, 0 to pi. The phi variable, this one, ranges from 0 to 2 pi. Now, the structure of this Hamiltonian is there are 2 terms. One term contains the variables theta and phi. The second term contains x variable. And the variables in this part are not present in that part. So whenever you have a sum of terms in the Hamiltonian expression with this property, you say directly the variables are separable. Separability means the solution of this problem. The total energy, rotational and plus vibrational energy, total. Rotation vibration energy is a sum. It's a sum of rotation energy plus vibrational energy. Such that this rotation energy is the expression B times J plus 1 that we have already studied, where with J equals 0, 1, 2, etc. The vibration energy is allowed values to put here. And this the explicit expression, this one, plus that, gives explicitly the allowed rotation and vibration energies. Corresponding to these energies, the rotation and vibration function, rho vip, is a product. It is psi rotation times psi vibration. This is product. Now let us examine the total rotation and vibration energy, B times J plus 1 plus F0 times V plus 1 over 2. Here J goes from 0, 1, 2, etc. and vibrational quantum number also 0, 1, 2. It goes on like that. Now, to understand this expression better, we need to have some idea about numerical value of B relative to F0. Now, we had used okay, for the molecule, HCl with 35 isotope, B value and F0 value in the same unit, wave number units. This is 2990.95. B value was in our rotational, all right, 10 points in same unit, wave number unit. Okay, now take this as 10. This one as 3000. You see that this is a vibrational property, vibrational quantity. This is rotational constant. The vibrational constant is 3000. The rotation constant is only 10. So vibrational constant is how many times larger than the rotational constant? 300 times, isn't it? So when we draw it, now, this is first indicate this part on the energy level diagram. This is 0.5 F0 at 1.5 F0. This difference is 3000 in wave number units. Now, because B is very small, you add up this part. For J equals 0, it has no contribution, because when J is 0, this is 0. For J equals 1, 2B, there is a level here. Draw this a little bit. This is J equals 1. The value is this number plus 2B. For J equals 2, this is 2 times 3. All these rotation levels belong to lowest vibration level. We repeat this for the first vibration level. You just take these and copy here. These levels belong to, these rotation levels belong to this vibration level, the first excited vibration level. All I'm doing is I'm drawing this formula, this expression, as an energy level diagram, using the fact that B is much smaller than F0, so that such differences is much smaller than differences between rotation energy levels. All right, we'll continue.